Welcome Stats 200 students to the second half of Lecture 14. In this half of the lecture, we're going to talk about sampling distributions and estimators. The main objective of this section is to understand the concept of a sampling distribution of a statistic. This is a vastly different topic than we talked about before in the last half of this lecture, the previous half of this lecture, where we talked about applications of normal distributions. Okay, so we will also see that some statistics are better than others for estimating population parameters. A big note here, this lecture is all about samples and sampling statistics, okay? This is a difficult and somewhat confusing topic. I hear somebody on the other end saying, yeah, the rest of them have been all easy topics, right? No, I understand that, but bear with me. This is a difficult and confusing topic, so I'm hoping to help dispel the confusion in this lecture. Okay, so we're going to start off with the definition. The sampling distribution of a statistic, such as the sample mean or a sample proportion, is the distribution of all values of that statistic when all possible samples of the same size n are taken from the same population. It's a very, very confusing definition. Okay, I completely understand that. This is typically, and then the second part here says, this is typically represented as a probability distribution in the format of a table, histogram, or a formula, which is the same stuff we've used before. Now, the sampling distribution of a statistic is the distribution of all values of the statistic when all possible samples of the same size, little n, are taken from the same population. So what does that mean? That means that, okay, we are going to keep sampling from a distribution, but we're going to keep our samples the same size n, and then we're going to compute some statistic from that. Say the sample mean, the sample proportion, or the sample variance. We're going to do this over and over and over and over and over again. And when we do it over and over and over again, we're going to take the mean of that statistic that we just computed, and that should give us a very close estimate of the actual population parameter. Okay, that may not make sense right now. I'm going to go through some more definitions, and then we're going to look at an example which I think will help enlighten you on this topic. The sampling distribution of the sample mean is the distribution of all possible sample means with all samples having the same size n taken from the same population. Wow, that is still just very confusing. It's a bunch of words, just a definition. Okay, bear with me as we go through this. And then as we do a couple of more definitions, we'll look at an example which will help explain this in more detail. Now, before we go into more definitions, we're going to talk about the probability of the sampling distribution of the sample mean. Sample means target the value of the population mean. This is important. This is saying that the mean of the sample means is the population mean, or it targets. In other ways, instead of saying it targets the population mean, it'll be very close. Okay, there's a lot of means in there. That's just a mean sentence. The mean of the sample means is the population mean. Okay, so what is this saying? If we take the mean of a whole lot of sample means that we have computed by sampling over and over and over and over and over and over again, then we're going to get a value that's very close to, or that targets, our actual population mean, which is what we are looking for when we do this. Okay? The expected value of the sample mean is equal to the population mean. The expected value, remember, the expected value, E, is equal to the summation of x times the probability of x. That's one way to do it. So the expected value of the sample mean is equal to the population mean. So we will apply that in just a little bit as well. Okay, the distribution of the sample mean tends to be a normal distribution. That's important. We're going to look at an example of this in just a minute. Now, the sampling distribution of the variance is the distribution of sample variances with all samples having the same sample size n taken from the same population. So before we were talking about the mean, now we're talking about the variance. Okay, do you remember the equation for a variance? Hopefully you do. We will look at that in just a minute. So this is assuming that we can figure out the variance. Okay. Sample variances target the value of the population variance. So what is this saying? It's saying that when we sample from a larger population, we collect a sample. We're going to compute the variance of that. We are trying to estimate the value of the actual population variance using this sample. That's the whole point of why we do sampling and why we're doing this. Okay, so if we just take one sample and compute the variance, we have a rough estimate for the variance. But what if we take another sample that's the same size and we compute the variance again? And then we do another sample that's the same size and we compute the variance again. So now we have 3 sample variances. Then we do another sample and compute the sample variance. So now we have 4 sample variances. And then let's do it again. Let's take another sample and compute the sample variance. Now we have 5 different sample variances. If we take the mean of those 5 sample variances, that's going to give us an estimate of the population variance. Okay? The expected value of the sample variance is equal to the population variance. So again, we're sampling over and over again. We're collecting multiple different variances, and they're not all going to be the same value. We're doing this over and over again. We're collecting information, and then we're going to take the mean of all of those, whatever computation we're doing, whether it be a mean itself, whether it be a variance, or whether it be a proportion, and then we're going to use that to estimate the actual population parameter, which is in this case the variance. Now the distribution of sample variances tends to be a distribution that is skewed to the right. Okay, so we talked about the sampling distribution of means. That was the first one. Now we talked about the sampling distribution of variances. And now we're going to talk about the sampling distribution of the proportion. It's the distribution of sample proportions with all samples having the same sample size n taken from the same population. Now, what do we mean by proportion? So we're going to have to define some terms and some notation first. So we need to distinguish between the population proportion, which is P. Oh boy, so now we're using P, which again, when we had a binomial distribution, remember P was a probability of success. So this is something different. Now this is the value of a proportion. P is the value of the population proportion, and P with this little caret above it, which is pronounced P hat, so it's P with a little hat on it, is the sample proportion. Okay, now sample proportions target the value of the population proportion. That is, the mean of the sample proportions is the population proportion. The expected value of the sample proportion is equal to the population proportion. Same kind of thing that we had with the sample means. Okay, in this case, the distribution of the sample proportion tends to also be normally distributed like that of the sample means. Okay, now why do we care about this? I heard you in the back saying, I don't care about this, why am I doing this? That's a very valid question, that's fine. Okay, this is a confusing topic, but hang with me. When we look at an example, I think it will make more sense. So after we do the example, I want you to go back and listen to the first half of this again and see if this makes more sense. Well, our sample means, our sample variances, and our sample proportions are unbiased estimators. That is, they target the actual population parameter. So these statistics are better in estimating our population parameter than some of our alternative statistics, which don't do as good a job. For example, sample medians, sample ranges, and sample standard deviations are biased estimators. they do not do a good job of targeting our population parameter. So just kind of FYI, the bias of the standard deviation is relatively small in large samples, so we often use S as an estimate of sigma, even though it's a slightly biased estimator of sigma. Okay, but again, sample medians, sample ranges, and sample standard deviations are biased estimators, which means they're not as good at estimating the actual population parameter. Okay, so all that information, confusing as all get out. I understand it. So here we're going to look at an example. We're going to repeat this process. We're going to roll a single die. Die is a single term for multiple dice. Okay, I want you to compute the theoretical mean x bar, the theoretical variance s squared, and the proportion of odd numbers of the results. And note, this odd number only applies to part C. Now, what am I saying by the theoretical mean? So we roll a single die. I want you to make note of the value on that die. So we're going to roll it. It's a 2. Okay, that's a 2. Roll it again. Now it's a 3. That's a 3. Roll it again. That's a 2. Okay, so we're writing this down. We first rolled a 2, and then we rolled a 3, and then I just jumped to somewhere completely different. Jumped way ahead. So apparently I'm writing too far down here on the bottom. So let me move this up a little bit. So we first rolled a 2, then we rolled a 3, then we rolled a 2. Let's say we roll again. Oh, now it's a 5. Roll again. Hey, there's a 2. I'm not sure that our dice are weighted since we got so many 2s. And then we rolled a 1. So this is telling us to what we're wanting when we compute the mean. We add all these up and divide by 6. That's what the mean is. Oh, I'm sorry, we're only rolling it. How many times are we rolling it? In this case, we rolled it 6 times. So we would add 2 plus 3 plus 2 plus 5 plus 2 plus 1, which gives us 5, 6, 7, 12, 13, 14, 15. So 15. And if we divide that by 6, we end up with 5 halves as our estimate for the mean in this case. So 15 over 6 equals 5 halves equals 2.5. So that's our estimate for the mean. Now, what do we know about the behavior of the sample means, sample variances, and sample proportions that are generated as this process continues indefinitely? The means of these sample values approach the true population parameter. So first, let's compute the theoretical mean of any roll. Well, how do we do that? Well, and this is the theoretical mean of the number of pips or dots showing on the dice. So mu is equal to the summation of x divided by n. Okay, so we're going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6 that's supposed to be a plus 5 plus 6 divided by 6. So we get, what do we get? 7, 14, 21 divided by 6, which is 3.5. Okay, so that's nice. There is our theoretical mean. We know that the actual population mean should be roughly 3.5 because that's the theoretical mean. Now we're going to compute the theoretical variance for any roll. Sigma squared, remember the variance equation? It's the summation of x minus the mean squared divided by n. Okay, so what do we have here? We're going to have 1 minus 3.5 squared plus 2 minus 3.5 squared plus 3 minus 3.5 squared plus 4 minus 3.5 squared plus 5 minus 3.5 squared plus 6 minus 3.5 squared. And all of that is going to be over 6. Here it is a little bit cleaner. So if we do 1 minus 3.5, that gives us negative 2.5. Square that is 6.25. So we end up with 6.25 plus 2 minus 3.5 is negative 1.5. Square that and we get 2.25. 3 minus 3.5 is 0.5. Square 0.5 and we get 0.25. Sorry, negative 0.5. Square that and we get 0.25. 4 minus 3.5 is going to be 0.5. Square that and again we get 0.25. 5 minus 3.5 is 1.5. Square that and we get 2.25. And 6 minus 3.5 is 2.5. Square that and we get 6.25. We're going to divide all that by 6. And if we work that out, we should get 2.9. So that's our theoretical variance. So sigma squared equals 2.9. Okay, now I want you to compute the theoretical proportion of odd numbers of any roll. All right, so this is kind of confusing. This concept of a proportion is kind of confusing. So the theoretical proportion of odd numbers of any roll. Well, the proportion of odd numbers on any roll is 3. 3 out of 6. So the proportion is 3 divided by 6, or 1/2, or 0.5. That's the proportion of odd numbers that we could expect on any roll. All right, hopefully that makes sense to you. Okay, so those are the computed theoretical values. What if we generated a sample on each problem by rolling a die 5 times and then compute the sample statistic on those 5 rolls? We just did it a minute ago on 6 rolls, but let's say that we only roll it 5 times. And then we repeated this process 10,000 times. So we actually roll the dice 50,000 times. Because rolling it 5 times is one sample. Rolling it 5 times again is the second sample. Rolling it 5 times again is the third sample. So we repeat this process 10,000 times. This is known as a Monte Carlo simulation. What would be the computed mean of the parameters? Well, we expect the resultant values would be very close to our computed theoretical values, since the computed values are the best unbiased estimators of the population parameters. So our sampling distribution values, the means of our sampling distribution values, should target the population parameter, which is equal to the value we found when we computed the theoretical values. Okay, so let's look at this a little bit more. So somebody actually did this. They rolled 5 die, and then they found the mean value of the number of pips showing. We know, because we computed it, that the population mean is 3.5, because we just computed it a minute ago. Well, here, sample 1 gives us a mean of 3.4. Sample 2 gave us a mean of 4.4. Sample 3 gave us a mean of 2.8. And so, going on. So these results are completed 10,000 times. All right, so this is done over and over again, and then the mean is computed at 3.49, this value up here. That's what they found after they took the mean of all these sample means. If we continue on indefinitely, the sample mean will be exactly 3.5. That is because the more we do, the closer we get to our actual targeted value. But 3.49 is actually very close. Notice that our distribution is shaped what? It's approximately normal. Okay, so this is a sampling distribution of means. We roll 5 die, we roll a die 5 times, or we roll 5 die all at once and then count the number of dots showing. Okay, or we roll a die 5 times and add up the number of dots and then divide by 5, the total number of rolls we have. Okay, so that's where we get this. Now, we can do the same thing with our sample variances, our S squared. We can roll 5 die and then compute the sample variance S squared. We found when we compute the theoretical value of sigma squared, that it's equal to 2.9. We can do this 10,000 times, and they found that the mean of the sampling standard deviation, the sampling variances was 2.88, which rounds up to 2.9, but it's very close. So if we continue indefinitely, the sample variance will be exactly 2.9. And this distribution is skewed with a longer tail on the right, so it's skewed to the right. So again, we take a bunch of samples, we find the variance of each sample, and then we take the mean of all of those sample variances, and that targets the actual population variance, which is what we were trying to do. We do the same thing with the sampling proportion. Roll a die 5 times and find the proportion of odd numbers that we get. So this is either yes or no. Either we get an odd number or we don't. Okay, so then we divide by the total number of rolls. So we count the number of odd rolls we get. So if we first roll a 3, then we roll a 2, then we roll a 5, then we roll a 1, then we roll a 4. Count the number of odd rolls. We have 1, 2, 3. So this is 3 out of 5. So that would give us a value of 0.6. Okay, 0.6, which is down here. Okay, so you notice there are only 1, 2, 3, 4, 5, 6 possible outcomes for this. And why is that? Well, let's say that we're using that at one point we get really lucky and roll all 2s. So we roll 5 2s. 2, 2, 2, 2, 2. Well, in this case, how many odd numbers did we get? We got none. So 0 out of 5. That puts us down over here in the 0.0 category. Now, if we roll all 2s and then roll a 1, now we have 1 out of 5, which is 0.2. So that's over here. That's 0.2. Okay, now what if we roll 3 2s and then 3 3s? Now we have 2 out of 5, which is 0.4, which is over here, right? So I hope you're understanding how we're getting these populations, these proportions. So if we roll 2 2, 5 3 3, now we have 3 out of 5, which is 0.6, which is down here. All right, and if we roll a 2, and then a 1, a 5, a 3, and a 3, now we have 4 odd numbers out of 5, which is 0.8, which is over here. And then last, if we get lucky somehow, and we roll 5 1, 5 3 3, we rolled 5 out of 5 odd numbers, which gives us 1.0. And that's over here. So this is the proportion. This is what we're doing when we're computing the proportions. And that's why these values are all fractions between 0 and 1. You should never have a proportion that's greater than 1. Because, what are the chances that I roll 6 odd numbers when I roll a die 5 times? 0. What's the probability, or what's the probability that I roll -1 odd numbers when I roll a die 5 times? Again, 0. You're not going to roll negative numbers or have a negative number of odd numbers. Okay, all outcomes are equally likely, so the population proportion of odd numbers is 0.5. The proportion on 10,000 trials here also actually came out to be 0.50. If we continue indefinitely, the mean of the sampling proportions will be exactly 0.5, which they already are. And also notice that this distribution is approximately normally distributed. Now, why do we sample without replacement? Why sample with replacement? Sampling without replacement would have a practical advantage of avoiding wasteful duplication whenever the same item is selected more than once. However, that's not necessarily the best thing to do. We're interested in sampling with replacement for 2 very important reasons. When selecting a relatively small sample from a large population, it really doesn't make any difference whether we sample with replacement or without replacement. We talked about that earlier. Remember, if we have n little n being less than or equal to 0.05 times big N, what's the difference here? Little n is our sample size, big N is our population size. If we have little n being less than or equal to big N, we can sample without replacement and treat it as independent events, and that's okay. So sampling with replacement results in independent events that are unaffected by previous outcomes, and independent events are easier to analyze and results in simpler calculations and formulas. So that's why we do that. But remember, we can treat these as independent events if we have this as well. Okay. Caution. Many methods of statistics require a simple random sample. We talked about how to get a simple random sample back in lesson 1. So if you use voluntary samples, convenience samples, or some of these other samples, this can easily result in wrong or skewed results. Okay, here's an example for you to try. When 2 births are randomly selected, the sample space for genders is boy, 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 girl, girl, boy, girl, girl. And I want you to assume that the outcomes are equally likely. First, I want you to construct a table that describes the sampling distribution of the sample proportion of girls from 2 births. Does the mean, and then for part B here, does the mean of the sample proportion equal the proportion of girls in 2 births? And then part C, does the result suggest that a sample proportion is an unbiased estimator of a population proportion? So step 1, construct a table that describes the sampling distribution of the sample proportion of girls from 2 births. So go ahead and pause the lecture and construct that. Now, if you don't have any idea what I'm talking about here, what I'm asking you to do is to compute a table that has sample and then the outcome boy, 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 girl, girl, boy, girl, girl, what the proportion is, and this is the proportion of girls from 2 births. So the proportion of girls in boy, boy is 0 out of 2, which gives us 0. The proportion boy, girl is 1 out of 2, which is, well, or, yeah, that's just 1/2. I'm kind of writing it. Or in here, again, 1 out of 2, which is 1/2. And here we have 2 out of 2, which is equal to 1. We said that the probability of each of them is equally likely. All right, the probability that each outcome is equally likely, so this is 1/4, 1/4, 1/4, 1/4. Okay? So that's the first step. Well, now I want you to look at the proportions. We have proportion here of 0, 1/2, and 1. So we have 3 possible proportion outcomes. So we use this to convert to a table that's the sample, then the proportion, and then the associated probability. I'm running out of room here because I wrote a little too big. I'll erase this. And we'll just come over here. So we have the sample, we have the proportion, and then we have the probability associated with that. So my sample, the first one, is boy, boy. The proportion of that is 0, and the probability of that is 1/4. My next sample is boy, girl, or girl, boy, which gives me a proportion of 1/2. The probability associated with that is 1/2, because we add up these 2 quarters here. And the last one we have is girl, girl, which has a proportion of 1, and the probability of that is, again, 1/4. Okay, so if you want to look at that a little cleaner, here's what it looks like. Now, does the mean of the sample proportion equal the proportion of girls in two births. So how do we do that? Now remember, mean, expectation, same kind of thing. So here we're going to have the mean of my sample proportion is going to be the summation of each individual proportion times the probability of that proportion occurring, which is the proportion value of the first one was 0 times 1/4, that was the probability, plus the proportion of the second one was 1/2, and the associated probability was 1/2, and the third one was 1, and the associated probability was 1/4. So this gives us 0 plus 1/4 plus 1/4, which is 1/2. Okay, so I'll just show you the answer here now. So because each gender at birth is equally likely, the proportion of girls in two births is 1/2. Thus, the mean of the sample proportion does in fact equal the proportion of girls in two births, which is what we found. So that's what we're getting at when we're talking about sampling distributions and sampling proportions. Now, part C, does the result suggest that a sample proportion is an unbiased estimator of the population proportion? And yes, it does. This result suggests that the sample proportion is an unbiased estimator of the population proportion. All right, there's a lot of information in sampling distributions. It's a difficult topic, I understand. Now, if you didn't understand all this, I recommend you go through the lecture again, read through the readable notes. Actually, first read through the readable notes, then go back and listen to the lecture again and see if it helps you understand all of the information. Okay, so this wraps up lecture 14. So we are still in lesson 6 next time. We are going to continue to examine more continuous probability distribution methods. Specifically, next time we're going to look at central limit theorem and then different ways to assess normality. All right. Thank you very much for your attention, and I hope you have a great day.